Went to a show Saturday night. Yeah, went to Fox Theater, saw a whole hour.
I was at sea.
Oh, really?
Yeah.
And you were like 2 blocks away. That's hilarious.
Look, there's a theater there. And I said, cool.
Yeah. Yep. I was there Saturday night. The weirdest time I met somebody that I knew in a really random place was I went to London, or I went to Europe after I graduated with a buddy of mine, and in London saw somebody I knew in high school. Just on the corner waiting for the subway. Yeah. It was really, oh yeah. Yeah, it was really bizarre. Anyway, it has nothing to do with class. It was just, I thought it was music.
You know what else is nothing to do with that?
Moana. Oh, she still wants to watch the Moana.
I mean, now it's stuck in my head. So
I told you.
I mean, I can play it on my phone, but then everybody...
No, the only thing that's stuck in your head, Marshall, is getting back to your house by 2:07 to watch the start of the Cardinals game.
That's true. That's the only thing I care about right now. That Cardinals game.
I know. I'm well aware.
Trying to even up the series to 2-2, Dr. Joe.
I know they are.
It's a big Hudson day.
Is Dakota Hudson the one pitching today?
Hudson and Keiko.
Keiko going on 3 days? Is Keiko going on 3 days rest? Did he do like game 1?
I thought
Part? Okay. Yeah.
I'm not 100% sure.
Okay. Other questions about things? Since I'm guessing not everybody cares about baseball. Yeah, Sam.
How do we set up the problem that I got points off?
More of a cubbies.
How did you?
Point 12.
For that one, when you were doing the probability with the 4th one on the 12th draw, you need to do 3 and 11. So you would do, what was it, 7? So it'd be 7 choose 3, and then 13 choose 8 over 20 choose 11. So that'll guarantee you'll get 3 in the first 11, and then multiply by making sure that you get one of the remaining defectives out of the last 9.
Yeah, he was off 3 days rest, Dr. Joe.
No, okay. That's what I thought was going on. Yeah, we did part of it. So the reason why you have to do it this way is because you want to make sure that you get the 4th one on the 12th draw. So I have to do exactly 3 and 11 draws and then the 4th one. So the conditional probability idea. And I can't use negative binomial because things are being selected without replacement. Other questions?
Not yet.
No.
Just wait till tomorrow.
Just wait till tomorrow? You just wait. All right, so we talked about Poisson distribution.
We use a different color here, Dr. Joe.
Let's use purple.
This one's not shiny enough.
Oh, I can use purple. How about purple? Purple?
I like purple.
Okay.
Reminds me just of me.
Reminds you of Justin Bieber?
Yeah, I don't know why. Whenever I see purple, that's just what my brain is. Weird, but just sharing.
Wow, that's. I don't know what to do with that information.
He has so much wine. It's not all about legendaries.
I don't know.
All right, so we finished up Poisson last time. That's what your homework is on for Wednesday. Today we're going to start our discussion of continuous random variables. So switching over from discrete random variables over to continuous ones. So the stuff that we've been doing so far with, say, the binomial distribution of selecting or having a certain number of successes in so many trials. The number of successes is a discrete number, right? 2, 3, 4, whatever you have. Or you found the first success on the nth trial, that was geometric. Or you had the kth success on the nth trial, that was a negative binomial. Or a certain number of occurrences during a time period, given an average time period, that was Poisson. All of those are counting number of occurrences. Those are all discrete ideas, right? But of course, not everything is a discrete idea that we want to talk about probabilities for. Maybe we have waiting time until the first thing happens. Well, time is certainly infinitely divisible, so that was an example of a continuous random variable. Or perhaps you're measuring heights or weights of things. Well, those are also infinitely divisible, so that would be a continuous random variable. So that's what we're going to start today, is just the theory behind continuous random variables. And then we'll get into specific distributions that have to do with being continuous random variables over the course of the next few sections in the book. So this is actually section 3.3 in your text, just to let you know where we are. All right. So the idea behind it is, pardon me, goodness. Remember we had the idea behind the probability mass function for discrete random variables, where we said that your f of x's had to be all positive for all your x's in the support. We said that if we did the sum of the f of x's over the support, we got 1. And we said that if A is a subset of S, then the probability that little x is in A, or capital X is in A, I should say, is equal to the sum for all x's in, not S, A, of your f of x, right? Those were our properties that we had for probability mass function. Now we're going to have similar properties for continuous distributions, and you might guess what they are. Actually, they're exactly these same ideas, but thinking about doing a sum of a continuous function isn't really a summation anymore. It'd be more of a limit of a sum. And when you think about doing kind of a summation over a subset, if you will, for a continuous random variable, what kind of a thing do you think we're going to do instead of doing a summation? If we think about doing a kind of an infinite sum idea for a function, what kind of a thing are we going to do? We're going to do an integral, yeah. So that's how we're going to calculate our probabilities for for continuous random variables if we're looking for probabilities. So for what was referred to for continuous random variables, we call a function f of x a probability density function. Or PDF for short, if it satisfies 3 properties. The first one is that the function is greater than 0 for all x in the support. We want to do the same kind of, that was the first property we had that's just off the screen. The second one needs to match what the PMF was. This says if we sum over everything in the support, we should get 1. Well, for the support, for continuous random variable, the summation over the support would be if I take the integral over all x in the support of f of x, I should get 1. Oops, real notation, dx. And the third one, I have to be a little bit more careful because I don't want to just say I have an arbitrary subset here. I want to talk about actually computing a specific subset. So this one will say if the interval from A to B is in the support, then the probability that x is in that interval is going to be the integral from A to B of f of x dx. So that's the idea behind a probability density function. You can probably think about why this matches up with the ideas that we were doing before for discrete things. Think about how you first came up with the definite integral. You started off by looking at area under a curve. Said, well, that's hard to do. So you chopped it up into pieces and then calculated the heights at specific values and then areas, right? and then added up all those areas and did more and more rectangles. And it's called the limit, the integral. Right? It's the same kind of concept here. I think about taking my probability density function. Certainly the probability that you actually land on one of those points is 0, because it's continuous, right? If I say pick a number between 0 and 1 at random, you're never going to think about the one that I'm thinking of, because there's way too many. 0. Nope, that's not it. So you're just never going to think about the one that I'm thinking of, because there's just too many of them. There's an uncountable number of numbers in the interval from 0 to 1. Okay? So the probability that I actually select a particular value is 0. However, if I think about chopping it up into intervals, and make sure that I add things to 1, I can again say, okay, for this interval, I'm going to give it a mass of one particular height. Well, it's the same idea as doing height times width and getting area. Right? And you integrate over the whole thing, you will get the probability. So that's the idea behind how we're getting these probability things. We think about chopping up the function into small pieces and doing a specific value over a small interval, giving us, multiplying those two things together to give us the appropriate probability. And then, of course, as you make those intervals get smaller and smaller, and doing those summations, that's where we're getting the integral from. So let's see if we can put this into practice a little bit. Let's look at, see, on your work handout that I just gave you, let's look at number 5.7. It's on the second page. There are some discrete ideas in this particular handout, so we won't be doing all of these. So I want to look at 5.7. So in this particular example, it says that you're going to be waiting for a bus. It tells you that it's proportional to the function 1 over x, where x is between 1 and 20. So this is a fairly common start of doing a continuous random variable problem. They're telling you something about the PDF, but they're not giving you the exact PDF. Okay? For example, if we check this, if we take the integral from 1 to 20 of 1 over x dx, antiderivative for 1 over x is natural log of x, absolute value technically, but we got positive numbers here for x, right? We'll just get log of 20, right? Notice that if I just integrate this over what they tell us the support is, I don't get 1, right? We agree? Right? Because what should this integral have been? It should have been 1, right? So instead of saying this was the function, it said it was proportional to the function, right? Or the probability should be a constant times this, correct? So what should our PDF be then to adjust for the constant that we got?
1 over L.
Yeah, we should get 1 over natural log of 20 times 1 over x, right? We did problems like this for the summation, didn't we? Where if I would have put the constant in here first, right? And then got a constant at the end and set it equal to 1. Remember doing the problems like that with the discrete ones? It's been a few weeks, but remember that? Where we said find the constant so that it became a PMF, and we used the fact that it had to add up to 1 to get the constant. It's the same idea here, right? This constant's out in front of my PMF. I know when we do this integral, I have to get 1. When I do the integral, I get c times log 20. So I have to divide both sides to get my c. So like I said, this is pretty indicative of the first kind of problems. The first kind of problems that you get in these continuous distributions. They're asking you to find a constant that makes it work as a PDF, a probability density function. By the way, if you're physics inclined, you should think of probability density functions just like you would of a density function, right? If I integrate a density function, I get mass. In this case, it's exactly what you get. It's just that if you integrate over the entire object, your mass is 1 all the time. It's the same concept in physics. It's also the same idea when we do expected value. It's center of mass. Same concept. All right. So finding the C okay? Does it make sense of why we had to do that first? Right? Because it didn't tell us what the PDF was to start with. Now we should be able to answer the question. It says, calculate the probability that you will wait 5 minutes or less. So how are we going to do that? Okay. I know my 5 is going to be my upper limit, right? Because it said 5 minutes or less. 1 has to be the lower limit. Sorry, I always forget to do that. 1 has to be my lower limit. Why? Why is 1 the lower limit here? Yeah, x is between 1 and 20, right? Now that tells us what the support is, correct? Okay. So the lower limit has to be 1. We've already done this antiderivative once. So in this case, we'll have natural log of x evaluated from 1 to 5, and this should give us log 5 over log 20. It is not log of a fourth. It's as good as you can get for simplifying that. Other than that, it's calculator time to get an approximation. Actually, I lied. You could write it as log base 20 of 5 if you really wanted to. I don't know why you'd want to, but you can write it that way. So you should get a decimal approximation. What do you get for a decimal? 0.54, is that what you said? Okay. Yeah, Sam.
What does this make sense? Does that mean that the time between 5 minutes and 20 minutes is less probability than 1?
Yep. That's what this means. Yep. So it says the bus is most likely going to be there within 5 minutes than having to wait more than 5 minutes. I mean, from the context, that's what it says. Yeah.
What if it's called the x of 1 was not have the equals to?
Okay, so if it had the equal to or didn't have the equal to, would it matter?
Yeah.
Like, you tell me, would it matter? If I integrate over a specific point, what do I get? Take the integral from A to A. Doesn't matter what A is. What do I always get? 0. So equal or not equal doesn't matter. It'll be the same answer.
So that first step where you found the C, if they don't outright give us a PDF, we're going to have to do that.
Yeah. Yeah, so either they'll put they'll have a C in there and tell you to solve for it, or say something like is proportional to. Okay. Let's look at 5.12. All right, so same idea here, right? They give you a function. They tell you, in this case, it is a probability density function, but they don't tell you what the C is. So the first thing we're going to have to do is figure out C, right? How are we going to find out what C is? What are we going to do? Yeah, let's do the same idea as the last one, right? We'll integrate over the entire support, which in this case is from 0.5 to 1.5, right? The function is, I'll pull the C out in front, x minus 0.5 to the 7th, 1.5 minus x dx. And that integral has to turn out to be what? 1. Good. Doesn't look like something fun right now to do. So I probably should rewrite the integral before I try to do it. In particular, what's causing issues? Within my mind, what's causing issues? This thing, I've got a binomial to the 7th power, right? There's a couple of ways I could attack this. I could do integration by parts. I could make this be my u and this be my dv. Because I can integrate that without any issue, right? I'm not going to do integration by parts because I don't want to. I'm going to make this. I'm going to make a u substitution instead. Let's let your u just be the inside. What's your du in that case? It's just dx, right? We agree? Now, of course, that doesn't necessarily take care of this, does it? But I can figure out what x is in terms of u, can't I? X in terms of u is x is equal to u plus 0.5. So I can plug that in here. So you get u to the 7th times this. I think you get 1 minus u du. Because again, this part here, this says x is equal to u plus 0.5. So I just plug that in here, right? So you get the 1.5 minus a 0.5. I also need to worry about my limits. What are my limits of integration now? If I change from x's to u's, what are my limits of integration now?
0 to 1.
Good. And then how'd you find those out?
Plug them in for x.
Good. Just need to plug them in for x, right? Plug in 0.5 for x, u is 0. 1.5 in for x, u is 1. And the reason why we do this now is because I can make my integral a little simpler just by distributing. That made life simpler, didn't it? Made my life simpler. I don't know about yours. Because now I can anti-differentiate both of those pieces. What do you get? Probably a 72nd.
Yeah, but I don't want to do that.
Well, that was 9 72nds minus 8 72nds. That one wasn't that hard. So the CSV 72.
Well, I got us that far. Somebody had to finish.
That's right. You did get us that far. It was a good job.
Back starting to hurt, Dr. Joe.
Carrying everybody, your back's starting to hurt.
this old Calc 1 integration is really
really taxing. All right. So C is 72. So that tells us again what our PDF is back at the beginning, correct? Just replacing the C with the 72. Now what's the problem ask? Okay, so if the staff meeting is longer than 1.2 hours, so our x is greater than 1.2. So what are we going to need to do that?
integral from 1.2 to 1.5.
Okay. Of the PDF. Now the good news is that we really don't need to reinvent the wheel. We've already done an antiderivative for this, haven't we? Right? When we did the substitution, notice that we, of course, when we did the substitution, these limits here were changed, right? What I just circled? What do I need to do to those limits after when we did the substitution? You got to subtract the 0.5, right? So if I want to write this out then, I would have 72. I would still have 1/8 u to the 8th minus 1/9 u to the 9th. That was the antiderivative, correct? Right? I want to evaluate this not from 1.2 to 1.5, but from what to what?
1.5. 1.2.
I don't, it's not 1.2 and 1.5 because we changed the variables, right?
0.7.
Yeah, 0.7 and 1.2. Because we subtracted 0.5 from the x's on those.
Why is that top?
That's 1, sorry. I thought somebody said 1.2, and I just mimic it. Whatever. Parroted it. You're right, it's 1. That's definitely a calculator problem, doing 0.7 to the 8th and 0.7 to the 9th. Well, somebody needs to get on it. I'm not doing it.
You just know 7 to the 8th power off the top of your head.
I don't. Sorry. It's 49 to the 4th. As useful as that is.
I got 0.80.
Okay.
Is that an answer?
Yeah, I don't think this one was multiple choice. Well, let's see if it makes sense.
Let me check my work.
Did you get the same answer? Let's see if this makes sense. Keyboard back on. So let's graph the PDF here real quick. So it was 72 x minus 0.5 to the 7th, and then 1.5, oops, hey, 1.5 minus x. Is that right? Hey, not too far. Oh, for heaven's sake. So, there we go. Come on. There we go. Good enough. Where's all the probability piled up if I look at this function? Where's it all piled up? Oops. There it is. It's over in here, right? Because we're doing integrals, aren't we? So here's about 1.25. So here's your 1.2, isn't it? So what this is saying is that we know that under the entire curve, the probability would be 1. The area should be 1, correct? So what this is saying is if I go from this line over, that's about 80% of the probability. Which from the graph makes sense, doesn't it? So 0.804 seems to be about right, about 80%. I would agree with that because this certainly looks much smaller. Pardon me. So what this particular thing is doing is it's weighting the probability much heavier on the right end of the interval than it is on the left. Much heavier on the right than the left. Does that make sense? Let's look at 5.8. To give another term that pops up in some of these problems. And to give us an idea of remembering some Calc 2 topic. Great. It's awesome, isn't it?
Actually, you already know I'm writing that.
Say that again.
So you already know I'm writing that.
Okay, so they give you a PDF again. By the way, this is a special type of distribution that pops up quite often, so you'll get used to this particular distribution and be able to solve the problems relatively quickly once you recognize that those are, oops, not greater than 100. Well, what type of distribution this is. So for this PDF, they tell you that we're only worried about x's are greater than 0. They also tell you, though, that the insurance coverage is subject to a deductible of $300. So what that means is that if X is representing the loss, the company's not going to pay squat until the loss gets to $300. And then they'll pay the difference between the loss and $300. So if you lose $800, if you have a claim for $800, they're only going to pay you $500. If you have a claim for $1,200, they're only going to pay you $900. It's like that's how your deductibles on your car insurance work, by the way. If you have a $500 deductible for collision and you smack into somebody, then you're going to have to pay $500 out of your pocket no matter what. And then they cover the rest. Okay? So in this case, it says, what's the probability that the insurance, what's the probability that the payment for a loss will be at least 100? Well, for the payment for the loss to be at least 100, what does the loss have to be at least? 400, right? So we want the probability that x is greater than 400, which would be the integral from 400 to what? Infinity. Good. Now, we could either do this by using the knowledge of improper integrals that you did back in Calc 2, or I could also use the fact that we could do a complement, right? I could do 1 minus what integral?
1 minus x is less than 300.
Yeah, I could do 1 minus x to x is less than 400, and you go from 0 to 400. Do it that way. This one, it's just as easy. I think it's just as easy to do either way. One thing I'm not going to worry about, I'm going to be lazy with my notation. Antiderivative here is just going to be negative e to the negative x over 1,000. Oops. It's a negative sign. Notice out in front, I've already got essentially the derivative of my exponent. When we do the antiderivative, the constant is going to go away. I got to adjust with a minus sign. Right. And well, this is where I'm going to abuse the notation. That's what we call it when we do it. When we don't write proper notation, we call it abusing the notation. I can't really plug infinity in, right? But that notation suggests that I'm going to plug infinity in. But really, what do I mean? I'm not going to plug the infinity in. I'm going to take a limit, right? Okay. But we already know how this limit works. As x gets really, 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 really big, this is e to a big negative power. What happens to e to a big negative power? What does it go to?
1.
It goes to 0, right? When a big negative power goes to 0, e to the 0 goes to 1, right? But this is big negative power, so it's going to 0. So really all we get here is e to the 0.4. 400 over 1,000.
You'll have to adjust for the negative.
It's 0. It'd be 0 minus a minus, so it makes it a plus.
Would it be negative?
Oh, it is negative 0.4. Yep. And there is negative in the exponent. Sorry. Thank you. There's no negative out in front, and that was what I was concentrating on. I forgot to put the one in the exponent. Thank you. It better be negative 0.4 because e to the 0.4 is bigger than 1, which would be a problem for probabilities. Yes.
Can you explain again where you're going over?
If I do a u substitution here, I would have my u as my exponent. My du would be negative 1 over 1,000. You just have the negative. Yeah. You have to adjust for the negative. This one okay? Like I said, this one was just as easy to do it straight as the integral as opposed to doing the complement. I could have done the complement, but... And actually, when you get more familiar with these problems, you probably will do this using the complement because we'll have another concept that goes with this particular topic And for this particular function, that concept is really straightforward. I know I'm being purposely vague because I haven't gotten to that point yet. Okay. All right. This one okay, though, for what we did? How we set it up? Yeah, Grace.
How are you getting to go to 0?
X gets really, 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 really big in the negative direction. So e to a very, very big negative is going to 0. Remember, negative means flip it upside down. So you're getting 1 over something very, very big. This is very, very small. That's what it's doing. Or
The whole thing's going to 0.
Huh? Yeah, the whole thing is going to 0, right? Say that again? Yeah, the exponent goes to negative infinity, right? Yeah, so we've got that horizontal asymptote to the left for the graph. When I think about it graphically. That's why. All right. So some other concepts that pop up, of course, with continuous distributions are the same kind of concepts that pop up in discrete distributions. So this is actually out of the book. So this is 3.3-4, part A. Let's say we have f of x is equal to x cubed over 4. For 0 less than x less than c, we want to find the mean and the variance. Well, just like we do mean and variance for discrete distributions, we're going to do the exact same thing for continuous distributions. The mean is the expected value of x. The variance is still using the formula, expected value of x squared minus expected value of x squared. Right? Those are the formulas we had for discrete distributions, correct? Same idea. So we can do the same thing here, of course. One thing that I probably need to know is what this c value is, right? How am I going to find out what that c value is to start with? Good, yeah. Integrate it from 0 to c and set it equal to 1, just like we did before, right? So we'll take the integral from 0 to c of x cubed over 4 dx equals 1. A little bit different, right? We didn't have a constant times the function. They actually put the constant in the interval. Antiderivative for x cubed over 4? Good. So we get x to the 4th over 16 evaluated from c to 0, which just gives us c to the 4th over 16. And c better be what then? 2. Good. All right, so that was the first thing we did, was just figure out what the c is, much like what we did in a couple of the other problems, right? The first thing we had to do is figure out exactly how we had a PDF. The first couple, of course, we had to figure out the constant to stick in front of the function. In this case, we actually had to figure out what that right-hand side of the support was, right? The right-hand side of the interval that we need to integrate over. All right, so now to find the mean, that's still expected value of x. Now remember how we found that for discrete ones. What did we do? We did the derivative of the moment generating function. What did you also do here? We don't have a moment generating function yet, though. Yep, we took x times the PDF, right? So same idea here, except that we'll have an integral instead of a sum. So we'll do the integral from 0 to 2 of x times the x cubed over 4, or x to the 4th over 4. Antiderivative for that's going to be what? Okay. And we'll evaluate that from 0 to 2. That gives us 32 over 20, so divide both top and bottom by 4, you get 8/5. If I did that right. So the mean, again, should be the balancing point. If we were to graph this, I'm not going to take the time to graph it, but if we were to graph that, there should be more probability piled on the right-hand side of the interval than the left. Does that make sense what I'm saying? There should be more area underneath the function on the right hand of the interval than on the left, because the mean the probability, it's more likely for a number to be above 1 than below because our mean's 8.5, right? If we run this experiment over and over and over and over and over and over, we get an average of 8/5. So that means there should be more probability piled up on the right-hand side than on the left. So if you graph that, that's what it should look like. This makes sense when you look at it. I mean, it's an x cubed function, right? It's going up like that. There should be more probability piled on the right than on the left, right? Just from your knowledge of the graph. All right, so then for the variance, we need expected value of x squared before I can do the variance. Again, same concept. Except that we'll multiply the PDF by x squared rather than x. Same idea, right? Notice really all we're doing is taking our same knowledge that we have from discrete distributions and sticking an integral instead of a summation. So then, antiderivative for this is going to be x to the 6th over 24. So we get 64 over 24, and dividing both, so you get 8/3. If I did my arithmetic correctly. Now for our variance, we'll do expected value of x squared minus expected value of x quantity squared. So 8/3 minus 8/5 squared. 75ths. 64 and 200. So 136 over 75. Okay. Okay, we'll call it 8. What did I do? Erase. Why won't you erase? Stop being a jerk. Erase. Okay, fine. We do it this way. 8? What did I do wrong? Oh, I didn't take 64 times 3. I didn't get my common denominator right. 64 times 3 is what? 192. Yes, I get 8 over 75. I just forgot a small arithmetic part. This okay?
Thinking, what was that symbol that you had? Was it S? Was that fine?
Mu. Mean and variance.
So
Mu.
I mean, we have to take the square root of that.
No, I said sigma squared. I didn't say sigma.
Oh, that was a question. Okay.
Oh, no. That's S squared. There you go. If you wanted the standard deviation, I would do the square root. You're right. We're okay with that? All right. So, yes, you can do other things like find moment generating function, do more probability types of things. We'll do more examples like this next time, as well as get into some actual distributions. So, since Marshall wants to make sure he gets to see the beginning of the Cardinals game, I'm going to let you out a few minutes early.
Thanks, Dr. Joe.
You're welcome, Marshall. Plus, I also have a meeting at 2, so helps me out as well. But all right, we'll see you.